Hello everyone, I'm Dr. Shanmuga Sundari, working as an assistant professor at PG and Research Department of Physics, Sita Lakshmi Ramaswamy College, Tiruchirappalli. In this session, we are going to see about the particle in one-dimensional box, where we are going to calculate the energy eigenvalues of the particle, which is confined in this one-dimensional box. So now we are going to consider a particle which is confined to move only along this x direction. And here one side of the box is completely fixed to the origin and the length of the box is a. And here the walls of the boxes are completely rigid, so it is not possible for the particle to penetrate through the wall, or if it wants to jump out of the wall also it is not possible because it should have infinite amount of energy to come out of it. So it is not possible to find the particle outside this box. So we can call this particle is confined in this particular one-dimensional box. And as we mentioned in this earlier section, the potential energy is infinite at x is equal to 0 and at x is equal to a. And v of x, the potential energy is 0 between this region. So for this kind of particle, now we are going to calculate the energy eigenvalue and how it is going to vary. Yes, so now we'll consider the particle is confined in this particular region between x and a. So for this particle, we know that the particle, I cannot find the particle when x is less than or equal to 0 and x is greater than or equal to a. So I can define my wave function psi of x is equal to 0 in this particular region. So only in this region I could find my particle. Okay, so I can use this Schrodinger's time independent equation, and we know that v of x is equal to 0 in this first region. So I can write the Schrodinger's time independent equation as minus h cross square by 2m del square psi equal to e psi, or I can write del square psi plus 2m by h cross square into e psi equal to 0. And here I'm just going to introduce a constant called k, which is nothing but square root of 2m by h cross square. So this equation can be written as what? Del square psi plus k square psi is equal to 0. Now I'm going to write the equation for our easy follow-up, that is del square psi plus k square psi is equal to 0. And this is a second order partial differential equation. The general solution of this kind of equation is given by psi of x is equal to a sine kx plus b cos kx. Here a and b are constants of integration. In order to find the values of this constant of integration a and b, we are going to use our boundary conditions. We know that the psi of x, the boundary conditions are nothing but psi of x is equal to 0 at x is equal to 0, and again at the boundary x is equal to a also psi of x vanishes. So by using these conditions only, we are going to calculate this constants of integration a and b. So now we'll first let us consider this equation is our first equation. So now we are going to use this first boundary condition. So when we are using it, then psi of x is equal to 0, sine 0 is 0 and cos 0 is 1. So we identified that b is equal to 0. So now we are going to substitute this b is equal to 0 in our equation 1. So it becomes psi of x is equal to a sine kx. So now we are going to apply our second boundary condition. When I'm applying the second boundary condition, again the psi of x is going to vanish. So I'll be having 0 is equal to a sine ka. So here we have two possibilities as far as this equation is considered. This equation will be 0 only when a equal to 0 or a sine ka equal to 0. What will happen if a is equal to 0? There won't be any wave function. So this condition is not possible. So the only possible condition is sine ka equal to 0. So we know that sine Ka equal to 0. When the sign Ka can be equal to 0, Ka equal to n pi, or I can write K is equal to n pi by A. So now we are going to substitute this K is equal to n pi by A in our equation 1. So it becomes psi of x is equal to A sine n pi by A into x. So this is going to be the wave function of this one-dimensional potential box. And here n is nothing but an integer which is taking the value from 1, 2, 3, 4, like discrete values only it is going to take. Why this n cannot be equal to 0? See, when n is equal to 0, what will happen to this k? K is also equal to 0. If k is equal to 0, what will happen to the energy? Energy also 0. So we know that the particle is having some energy, and we cannot find the energy, I mean, the particle which is having a zero energy. So that is the reason why n is taking the values from n is equal to 1 to 4. Now we are going to calculate the energy eigen value of this particle which is confined in this potential one-dimensional potential box. We know that k square is nothing but 2m by h cross square, and we know that k is equal to n pi by a. So from this equation, what we are going to do is we are just going to equate it. So which is nothing but 2m by h cross square is equal to n square pi square by a square, and we need to calculate the e value. So which is nothing but e is equal to n square pi square h cross square by 2m a square, and we know that h cross is nothing but h by 2 pi. So by substituting this value, we can easily calculate n square pi square by 2m a square into, for h cross square, I just going to write h square by 4 pi square. So this pi square will get cancelled. So final value E and the energy eigenvalue of this particle in one-dimensional box is given by n square h square by 8m a square. So this is the energy eigenvalue, and from this equation it is very clear that the energy eigenvalue is directly proportional to the n square, and here the h is a Planck's constant and a is the length of the box, and m is the mass of the particle which has been confined in this box. So the only variable here in this energy eigenfunction is our n. So now we are going to see about the conclusions of this energy eigenvalue. We know that the energy eigenvalue is given by just energy eigenvalue En is given by n square h square by 8m a square. So using this, we are just going to calculate the ground state energy of this particle. So the ground state energy means we need to substitute n is equal to 1. So the ground state energy is given by what? H square by 8m a square. So using this ground state energy, we can write the other energy eigenvalues. So say for example, if I want to write for the nth state, then it is nothing but n square into E1. So always the energy of the states are directly proportional to the n square. And the possible energy values are proportional to the discrete values of this n, means n is equal to 1, 2, 3, 4, etc. And now let's calculate the energy difference between the consecutive states. Yes, now we are going to calculate the energy difference between the consecutive energy states. So we know that En is nothing but what? N square h square by 8m a square. So what is the ground state energy? E1 is given by n is equal to 1. So it is going to be h square by 8m a square. Similarly for E2, it means n is equal to 2. So it is going to be 4h square by 8m a square, And similarly for E3, it is going to be what? 9h square by 8m a square. So the difference between this E2 and E1, which is nothing but I'm just going to subtract. So this is going to be what? 3h square by 8m a square, or simply I can write this is nothing but 3 into E1, because we know that this is nothing but my E1 value, right? The ground state energy value. And similarly for E3 minus E2, it is going to be 5h square by 8m a square, which is nothing but 5 into E1. Or in general, I can write n plus 1 square E1 minus n square E1 is equal to 2n plus 1 E1. So this is the energy difference between the consecutive energy states. So based on that, I can draw the energy level diagram. So based on the above equation, we are just going to draw the energy level of this one-dimensional potential box or potential well. So this is going to be my n is equal to 0, where we couldn't find any of the particles. So the ground state energy is given by n is equal to 1, where this is going to be my E1. And for n is equal to 2, so this is going to be my E2. And then for n is equal to 3. So this is the third level of my particle, and here is the fourth state of my particle. So here very well you can see that the energies are having the discrete energy values, and the energy gap between the consecutive energy levels goes on increasing as the n value is increases. So in the next section, we are going to see the orthogonality and the normalization of this one-dimensional potential box. So thank you for listening. Thank you very much.